All right. Good afternoon, everyone. I hope you are all very well. This is the second lecture of the course Design Practice, CVN 4002 and CVN 9000. In the previous lecture, I gave you an introduction to the project and the structure of the course. And after that, we started the first chapter of this project, which is about the evaluation of the strengths of the subgrade. So you remember that we have two types of soil in this project. We construct the new container port on the reclaimed soil. And also we have one existing natural soil, and the access road is on that, that soil. So the aim is to determine the value of CBR, the California bearing ratio for the soil, because most of the charts that we are going to use are based on CBR, which represent the strengths of the material, the strengths of the subgrade. And for mechanistic design, we will learn how to convert that CBR to the Young modulus, to the elastic properties of the soil. And also for numerical analysis, we need to have access to those elastic properties. So in the first phase of this project, we are working on subgrade evaluation. And for subgrade evaluation, I showed you different methods to determine these strengths, the strengths of the subgrade. And we went through the first method, the first testing method, which is the in situ CBR or the laboratory CBR test. In this lecture, we are going to find out how we can determine CBR from the dynamic cone penetrometer test results, and also how to use the classification tests, the results of the sieve analysis and Atterberg limit tests in order to determine CBR. During the lecture, also, if you have any questions, please write it down in the chat. And during the break time, I will go through your questions and I will answer. All right, briefly, I'm going to review this CBR test. And after that, I will continue the rest of the lecture. So for CBR test, you can conduct the test in the field, or you can bring the sample to the laboratory and conduct the test in lab. And I explained the definition of the CBR. CBR is the ratio of the strengths of the soil, the existing soil or the site soil, over the strengths of a well-graded crushed stone, which is called the standard material. And this table shows you the CBR test results on this standard material. So as you can see, the results are the penetration of the plunger versus the load. So if you want to penetrate 2.5 millimeter in this well-graded crushed stone, you need to apply 13.2 kilonewton. And we do the same procedure for the natural soil on the field. So this method, this CBR test, is only applicable for fine grain and medium grain soils. If the size of the particles are large, then in that case you cannot conduct this test. Here are the dimensions of the soil sample, and we need to apply a surcharge mass, and the value of this surcharge mass must be equivalent to the weight of the pavement. And then we start conducting the test. We are putting the piston with the diameter of almost 50 millimeter on the soil, and we start applying the load. And the rate of penetration for this is constant, it's 1 millimeter per minute. And during applying the load, we start recording the level of load. Generally, this is done automatically. About the drainage condition that you need to take into account, because if you conduct the test in the laboratory, you need to somehow consider the same testing condition as the moisture condition in the field. And that moisture condition in the field depends on different things, depends on the annual rainfall, the median annual rainfall, how much rainfall you have in that area, as well as the type of the drainage condition that you can provide for that road or for that pavement. So here, this is the table. We went through this one last week. If you can, for example, provide excellent to good drainage condition, you can even consider unsoaked sample. But if that's fair to poor drainage condition, then you need to at least soak the sample for 1 day, depending on the median annual rainfall. If the city that you're considering and designing the, for example, the road is considered as the city with heavy rainfalls, with over 800 millimeter rainfall per year, then you need to at least, soak the sample at least for 4 days. And you remember that the moisture content of the sample can significantly affect the CBR value. That is the reason we are trying to simulate the same drainage condition for the sample as it has in the field. So this is just the review. You remember it from the previous lecture. And eventually, after conducting the test, you will get such a curve. It is load versus penetration. So you can simply draw the curve. And there are two values that you need to read. One is the load relevant related to the penetration of 2.5 and the load related to the penetration of 5 millimeter. After reading these two values, you need to divide these values with the relevant standard loads. So the standard loads are coming from the table, 13.2 and 20.55. And you calculate the value of the CBR. So I showed you one example last time, 25 and, for example, 24.5. When the CBR 2.5 is larger than CBR 5, which is the case in this example, when CBR 2.5 is larger than CBR 5, the final CBR is CBR 2.5. But when CBR 5 is larger than CBR 2.5, the results are not that reliable. You know, it is maybe because of the testing error. The reason for that I say that this must be an error is that generally definitely the CBR value in depths, the strengths or the load level in depths is increasing. But this increase is not that significant. For the soil, the rate of for the existing soil or for most of the soil, the rate of increase in load is not comparable with the increase of the load for the standard material. For the standard material, we have much higher rate of increase in the level of load. Look at this one. From 2.5 to 5, the value increased from 13 to 20. So it is 7 kilonewton just in increase of depth of 2.5 millimeter. But in the field, generally, the increase is not that much. Look at here, for the natural soil in the example, the value increased from 3.35 to 4.9. So for most of the soil, CBR 2.5 is larger than CBR 5. If this is the case, then you can rely on the results. But if you derive CBR 5 larger than CBR 2.5, the Australian standard recommends that you need to repeat the test. If you repeat the test and again you get CBR 5 larger than CBR 2.5, then you can rely on your result and consider CBI as CBR 5. But otherwise, you need to consider your final CBR or the design CBR equal to CBR 2.5. So again, this is the review. We already covered this part, but this is the new part from this lecture. We conducted the CBR test, but we want to conduct, for example, numerical analysis. We cannot use CBR for the numerical analysis, or when we want to design pavement using the mechanistic approach. In that case, the parameters that we need to use are elastic parameters. The elastic parameters that we need to determine are the Poisson ratio, the Young modulus, as well as the stress parameter or shear stress parameter. For subgrade materials and in general for unbound granular materials, the behavior that you need to consider is elastic and transversely isotropic. It is not isotropic. The behavior is anisotropic, and in particular is transversely anisotropic. And the reason is because of the generally this anisotropic behavior is because of the sedimentation process. So let me explain what does it mean, this transversely isotropic. In isotropic case, let's say that this is soil and you consider just one point inside the soil. For isotropic case, the material parameters in different directions are the same. For example, in vertical and horizontal direction, the Young modulus would be the same in vertical direction and in horizontal direction. In contrast, for anisotropic material or anisotropic soil, the material parameters are the functions of the directions. They are changing in different directions. And in transversely isotropic in particular, the value in vertical and horizontal directions are different. So we have one EH in horizontal direction and one EV. And the reason for this is that the material parameters actually are stress dependent. You remember that from soil mechanics or from the fundamentals of geomechanics, that material parameters are stress dependent. And you remember that in different directions, the stresses are different. You remember more circle. So in horizontal direction, sigma h and sigma would be different from sigma v. Lateral pressure is different from the vertical pressure. Since sigma h is different from sigma v and Young modulus is the function of stress, then EH would be different from EV. And based on Ostro's, it is essential, it is important to take into account the effect of anisotropy. That is the reason that in isotropic test, we only have two independent parameters, E and nu. But in anisotropic or transversely isotropic case, we have 5 independent material parameters. 2 Poisson ratio, 2 Young modulus, and 1 shear stress function. But how can we determine these material parameters? You can still determine these material parameters based on the CBR test results. There are 2 very simple empirical equations from Ostro's that we are going to use here. One is determination of the vertical modulus, or EV. You can simply multiply CBR value that you derive by 10, and that will give you the vertical Young modulus. And based on Ostro's, there is a maximum value for that. You cannot consider larger value than 150 megapascal in your analysis. The second equation is for horizontal modulus. You can simply divide the vertical modulus by 2 and determine the horizontal modulus, or EH, and consider that in your analysis. So 2 very simple empirical equations provided by Ostro's for determination of the Young modulus in different directions. For Poisson ratio, we assume that the behavior is isotropic. So we consider the same Poisson ratio in different directions. But that depends on the type of the material that we are dealing with. If we are dealing with cohesive material, like clay, the value that we consider is 0.45. If we are dealing with sandy soil or gravel, or let's say silty soil, then we are dealing with non-cohesive material. In that case, you can consider 0.35 as the Poisson ratio. And the other one is the stress function, or shear stress function, which represent the shear modulus of the soil. And this can be calculated from this simple equation. It is the vertical modulus over 1 plus Poisson ratio. But the advantages of and deficiencies of this CBR test, the main advantage is that this is a very quick test and it is inexpensive. You can conduct all the tests within 1 day, and only you need 1 person to conduct the test. So very simple test. The test can be done, it's very flexible. It can be done in the laboratory, or it can be done in the field on different soil samples. And as I mentioned, you can get the results within a day, and you can perform it just by yourself, but the assistance of one excavator will be very helpful. And about the deficiencies or limitation of the CBR test, the main deficiency is that it is only applicable to fine grain materials. So, and that's because of the small diameter plunger that we are using. So we cannot conduct on the coarse particles. So do you have any question about the CBR test? All right, so let's talk about the next testing method that we are going to use in this project. The next test is dynamic cone penetrometer test. Here you can see the equipment. Again, very simple equipment. So again, very cheap, only can be done with one person, and you can get lots of result within a couple of hours. So you need to keep this shaft upright. There is one cone at the bottom, but the nature of the test is different from CBR test. As you can see as you can guess from the name, it is dynamic test. So you need to apply impact load. In the previous test, we had quasi-static loading condition, but here we have dynamic loading condition. We are applying the drop of a hammer. So you can put this shaft upright, then lift the hammer and drop it. And when you do this one, after 5 blows, you need to count the number of the level of the penetration. So this test has been designed to provide a measure of the in-situ strength. Again, this is mainly for fine-grained materials. Here you can see the schematic figure of the equipment. So it has one shaft, one cone with the inclination angle of 60 degrees and diameter of 20 millimeter. And there is one hammer, 8 kilogram hammer. So you can simply lift this one and drop it from one specific distance. And this distance between these two stops is 51 centimeter. And during the test, you measure the penetration. So here is the test procedure, and here you can see the equipment. They are doing the test in the field. So place the DCP point on the surface and hold the DCP upright and start. Just lift the hammer to the top and release it. So this is a dynamic test. The amount of energy that you're applying is important. So you shouldn't throw this hammer. Otherwise, you apply more energy to the system. So the results won't be reliable. Therefore, do not throw the hammer down, but let it drop. And we usually record the depths of penetration every 5 blows. And eventually you get the results like this. We generally continue the test until 800 to 1 meter, 800 millimeter to 1 meter below the surfacing. And then we draw the results. It is the horizontal axis is the number of blows, and vertical axis is penetration, millimeter. How can we determine this DCP? DCP is somehow the slope of this line. So in this, if I want to explain it very simple, the slope of this line will give you the value of dynamic cone penetration, DCP. But there is a procedure that we generally follow in order to calculate the DCP. And here I explained it in 4 stages. So you conducted the test and you got the results, number of blows versus penetration. So the thing we want to do is to determine DCP index, which is penetration per blow, and the unit is millimeter. So we calculate the DCP index, but after that we calculate the average DCP index. So the values, each of these points can give you one DCP index, but always there are some inconsistency, there are some errors. So they are not exactly equal to the average value, right? And there is some standard deviation. Higher level of standard deviation, it means higher level of error we had in the test. So somehow we need to take into account the effect of this error in the analysis. How can we determine that one? I'm going to show you. So in order to take into account the effect of error, we need to determine a standard deviation, and this is the equation that you can use to determine a standard deviation. So here we have the average value, and this is the value for the DCP value for each point. And after calculation of the standard deviation, you need to consider the average DCP minus 0.9 times of a standard deviation. And this becomes the final design DCP value. So you can see that, as I mentioned, this standard deviation somehow represent the error in the system. So higher level of error in the system, it means that you need to consider a lower value of DCP. So this is very straightforward procedure to determine the DCP. It is the average DCP minus a weighted error. But we derive DCP, and we know that most of the charts in Astros are based on CBR value. So Astros provided us one chart, very simple chart. It is log-log, both of the directions, the penetration is in log form, and also the vertical axis CBR is also in log form. So based on the DCP value, which is the horizontal axis, penetration millimeter per blow, you can determine the California bearing ratio. For example, if DCP is equal to 20, then the CBR value that we read is 10. So you can simply use this chart in order to indirectly calculate the CBR value. But what are the advantages and limitations of this DCP test? Again, similar to CBR test, it is low cost, it is fast. Also, the equipment is light and portable. It is easy to use, and you can learn how to do the test in a matter of minutes. You already learned how to do the test. You can conduct, generally the depths that you can do the test is considered as a large depths, large penetration depths. So generally we can conduct the test for up to 1 meter of the soil from the surface. And this is a very fast test. You can conduct a large amount of tests and derive a lot of results very quickly. The next test is, again, indirect way to determine the CBR value is by using the classification test results. You remember from soil mechanics or fundamentals of geotechnical engineering, fundamentals of geomechanics, that in order to classify the soil, we need to conduct some tests. We conduct sieve analysis for coarse material, and we conduct Atterberg limit tests for fine materials. For fine materials like silt and clay, the size of the particle is not important, does not control the behavior of the soil. For fine particles like clay and silt, the important thing is their behavior in the presence of water, right? So if it shows some plasticity, it shows plastic behavior, then it means that we are dealing with clay. If it doesn't show it is a non-plastic material, then probably we have high percentage of silt. In addition to these two tests, we have another classification test, which is called linear shrinkage test. So the test is simple. You put one sample of soil, you consider one sample of soil, you simply put it in a mold, and after that, so the length of the mold is a specific value. Then you put it in the oven for 24 hours, and when you bring it out, the sample has been shrink, right? So you can simply calculate the level of shrinkage and the ratio of the, so when you put it in the oven, it is L for dry, the length for dry, and we have L before dryness. I write it as L wet. So to calculate linear shrinkage, you can simply write it L wet minus L dry over length of the initial length of the sample. And that will give you the linear shrinkage. It is very straightforward test that you can conduct. And based on the results, there are two empirical equations that I'm going to show you here. You can see them here. And use these two empirical equations to indirectly determine the value of CBR. So this test, again, similar to CBR, is applicable. This method is applicable to the soil with fine grain. For the case, let me clear this part. For the case that more than 75% of the soil passing through the sieve size 2.36 millimeter. In that case, you can use this method. But the CBR value that you calculate is actually the CBR value for the soaked sample or for the soaked soil at 95% maximum dry density. So by using these two equations, you calculate CBR. But what is this CBR? For which type of soil we are talking about? This CBR value is for fine grain material for a soaked sample at 95% maximum dry density. Because you remember, the dry density, change of dry density and change of the moisture content will change CBR of the soil, right? So when you use this equation, the CBR value that you calculate is for the soaked CBR at 95% MDD or maximum dry density. And eventually you have two CBR. They won't give you the same value, of course. And in order to determine the design CBR or the final CBR, we use this equation. This equation is the weighted average weight to determine CBR. So we give higher weight 3, we give higher weight the minimum value and a lower weight, which is 1, to the maximum value. And then we divide it by the total weight, which is 4. So it is called the weighted average that we use. But what are the terms in this equation? P 0.425 is the percentage of soil passing through 0.425 millimeter sieve. So these are just the sieve size, the percentage of the material passing through this specific sieve. LS is the linear shrinkage in this equation, and PI that you can see is plasticity index, which is related to the Atterberg limit. That's the difference between the liquid limit and plasticity limit. All right. So if you have any questions, you can write it down. So they asked about any limitations of DCP test similar to CBR test. That's a good question. Thank you. I forgot to explain that one. Similar to CBR test, this is mainly for fine grain materials. So all these tests that I explained you here are for fine materials, for fine grain soils. That is considered as the main limitation of the DCP test. So let me show you one example. We have the sieve analysis, sieve test results, as well as the Atterberg limit test and linear shrinkage test results. The first thing we want to determine is that whether we can use this classification test method for determination of CBR or not. In order to check that one, we need to look at the sieve size 2.36. So this is sieve size 2.36. You can see that the percentage of passing from this sieve size is 98%. So 98% or less smaller than 2.36 millimeter. So this is okay. We can use the method. The soil is considered as the fine grained material. Next step is to use these two empirical equations. So the first estimate for CBR, this is this equation. So what we need in this equation, we need the passing percentage of 0.425. This is passing percentage for 0.425, which is 90%. We need the passing from 0.075. So you remember this from soil mechanics. This 0.075 from unified soil classification system is the boundary between fine materials and coarse materials. So the value is 14%. The passing percentage is 14%. Linear shrinkage is 0.6. And we have P 0.075, which we already have. So you can simply substitute and calculate. Because the first CBR value is 17.6. Now we use the second equation. In the second equation, again, the terms are the same, but we have two additional terms. One is P 2.36, the percentage of passing from the sieve size 2.36, and the other one is plasticity index. So now we need plasticity index 10, and also we need this 98%. You can simply substitute the value, and the second value that you can consider and you calculate is 9.4. So you can see the level of uncertainty. You can see how rough approximation is this method. The results that provide us, one is 9.4 and the other one is almost double, 17.6. So in order to determine the design CBR based on the classification test, you can use this weighted average method. So it is 3 times of CBR minimum plus CBR maximum divided by 4. You can simply calculate, and the design CBR based on classification test is 11.5. The other challenge that we have in order to determine CBR is when we have a weak layer below the surface. So we want to know how to determine the effective CBR in this case. If you somehow doubt that there is a weak layer below the surface, you need to continue the test for at least 1 meter below the top of the subgrade. So we need to determine the CBR value for at least 1 meter from the surface. After that, if there is a weak layer below the surface layer, in order to calculate the effective subgrade, we generally use Japan method. Again, this is very straightforward method. This is the formulation, the empirical equation that we use to calculate. I will go through your questions during the break time after finishing this part. So I will get back to your questions. So this is the equation that we can use. As you can see, again, this is the way the weighted average of the determination of CBR. So it's the function of the thickness of the layer, and it's the function of the CBR for each layer. The maximum value that you can determine based on this is 20. Also, there is one rule here. The layer must be greater than 0.2 meter thick. So the thickness of the layer you are considering at least must be 0.2 meter. The other rule that we have here is that the layers must be decreasing CBR. So the CBR value, if you want to use Japan method, the CBR value should decrease in depth, right? Otherwise, this equation won't be applicable. So let me show you one example, very simple example, how to use this Japan method to determine the CBR value for a soil or for subgrade with weak layers below the surface layer. So look at the results. There are 3 layers soil. The thickness are here, 0.2 meter, 0.5 meter, and 0.3 meter. And as you can see, the CBR is decreasing in depth, 8%, 4%, and 20%. So you can simply use the Japan method. This is the thickness of the first layer multiplied by CBR value to the power 1/3 plus the thickness of the second layer multiplied by CBR value to the power 1/3 and also for the third layer and divided by the total thickness. And as I mentioned, we need to conduct the test at least for 1 meter. So the summation is 1. And based on this, you can calculate the effective CBR, which is 3.8. And as you can see, this is much less than the CBR at the surface. So if you consider the CBR at the surface, that can cause the failure in the pavement structure, because the effective value or the design CBR is much less than that because of the presence of weak layers. These are some rules and some hints for determination and selection of design CBR. So the first rule is that in order to calculate the CBR in the field, you need to conduct at least 3 different testing methods. You need to consider 3 different testing methods. So CBR testing should be undertaken by 3 different methods. The other thing is that you need to conduct the test under the worst climate condition. So the field testing should be undertaken under worst climate condition, and generally the worst climate condition is after heavy rainfall, after the wet season, because you remember that the higher level of water inside the soil, generally the strength would be less. The undrained condition for the soil would be, or the undrained strength for the soil would be lower than the drain strength. There are also some hints that we need to consider. When you obtain the results and CBR values, look for anomalies and try to explain them. Always there are some errors in the testing results, in the data, in the experimental data that you have. So try to find them, try to explain them, and if you cannot explain them, try to use the conservative way and take lowest value if you cannot explain. First of all, if there is an error, eliminate that one, remove it from your result, right? And if there are two extreme cases, it is better that you use conservative judgment and consider lower value for the CBR. Another hint is about the case that you have strong subgrades. So various agencies in practice adopt a maximum CBR. For example, you conduct a test and you derive CBR 40. Can I use that CBR 40 for my design? The answer is most of time no. So there is a maximum, there is a cap for CBR. And that cap depends on the type of the soil that we are dealing with. Generally, the cap is defined, different agencies consider different values, but generally the range is between 10 to 15. If we are dealing with sandy soil, we generally consider maximum CBR as 10. But if the quality of the soil is high, it is a sub-base quality material, then in that case, we can increase the cap and we can consider 15 as the maximum CBR. This is for a case that you're dealing with a strong CBR subgrade. But how about the case that we are dealing with soft subgrade? This is for a case that CBR is less than 5. Generally, when CBR is less than 5, we have some problems and challenges regarding the construction. So because of that, we need to somehow improve the soil. When CBR is less than 5, generally we need to conduct some pre-treatment, but that is not a requirement. And if we don't improve the quality of soil, in that case, that can cause some delay in construction, in particular when we have rainfall. But when CBR is less than 3, then in that case, it is a requirement. You have to find a solution. Otherwise, we won't be able to construct, and the construction cannot be proceed. But which methods we can use in order to improve the quality of our soil? Here are some methods. First thing is to try to get rid of water by providing good drainage boundary conditions. Try to make the soils dry. In that case, you will have higher level of strength. The second is for the case that we are dealing with a thin layer. So the surface layer is a thin layer and it's a soft soil. So it would be easier that you remove that one, excavate it or replace it with a stable material. The other one is that you use gravel and rock and generate and make a gravel or rock working platform covered with impermeable capping. Again, we use one impermeable capping at the top in order to let water gets into the soil and decrease the CBR value. Another method is to use cemented working layer. Again, make the surface impermeable. The other method is to use some additive materials to the soil and stabilize the soil. the existing subgrade. The other methods is using geotextile and geogrids in order to improve the CBR value. Here I'm going to explain a little bit more about stabilization of the soil. Stabilization methods are for the improving the quality of the subgrade. So we want to improve the stiffness, we want to improve CBR value, and we want to improve the permeability. You remember, permeability shows the potential of the soil for passing water, right? So when the permeability of the soil is higher, water can go through the soil faster. So again, we can get rid of water more readily. And the other reason that we are using additives in order to stabilize the soil is that we want to reduce the water sensitivity. This is very important for reactive soils. For example, in Western Sydney, we are dealing with reactive soils. When you add water, the soil will expand. During the dry season, the soil will shrink. So large level of settlement, which is very problematic and cause failure in the road, in the foundation, and in structure. So you need to add some materials in order to stabilize, in order to reduce water sensitivity of the material. So this is the chart that you can use in order to decide which type of additive you can use for that one. As you can see, that's the function of the plasticity index of the soil and also the amount of fine grains in the soil. So for example, when we are talking about the coarse materials with less than, when we are talking about the coarse material with less than 25% passing the sieve size 75 micrometer. So this is for the coarse material, coarse grain material. And let's assume that the plasticity index is larger than 10. Then which material we prefer to use? It's cement for stabilization, also lime. So the black one shows that these two materials are suitable. So again, you can see that depends on the type of the soil that we are dealing with, whether we are dealing with a fine soil or coarse soil, and what is the plasticity index of that soil. All right, now there are some questions. If you have questions, we can go through them very fast, and after that I will explain the data. So for the DCP test in this assignment, should we use the gradient method by plot or calculate the standard deviation manually? So it is, you need to determine the standard deviation, but you can simply use, for example, Excel or MATLAB to determine the standard deviation. If I bring the result, so these are the test results, these are the DCP test results. Similar to the procedure that I explained, you need to calculate the standard deviation, and you can use different software, simply calculate the value. In the assignment, DCP tests are done at numerous locations. How we are supposed to consider those while we working out the design DCP. So this is very normal. You need to conduct DCP tests at different locations because soil that we are dealing with is non-homogeneous material. So we cannot just consider one specific point. But that depends on your engineering judgment, that there are some uncertainty. As I explained you, I gave you some tips that, for example, first you need to look for the anomalies, the errors, and try to get rid of those errors. Try to remove them from your results. And then based on the result, the reliable result that you have, And based on your engineering judgment, you need to decide which value is the design value. So in the lecture notes of 9525, 50% passing is considered as fine grained soil, but the rule here is 75%. So which rule? So yes, the definitions can be different. For example, in soil classification, unified soil classification system, there are some rules. We can consider, for example, 50% as a boundary of the fine material or coarse material. But in Ostrodes, and for the case, for the table that I showed you, the value is different. So this depends on the behavior during the test they have conducted, right? For the road, when they wanted to classify the materials, they use this one. But for the assignment, I mentioned that you need to use unified soil classification system for the second part. So if you are talking about that part, I specifically mentioned that you need to use unified soil classification. But if you are going to use the table I showed you, the table I showed you here, this is for the determination, this is for the case that you want to decide about the additive for the stabilization of the soil, right? Can we still use the Japan method if the total HI is greater than 1 meter? For Japan method, we generally consider the 1 meter of the soil. If that's below that layer, if we ignore that zone. So just for 1 meter. And that would be sufficient. That would be enough. That's the reason the results I provided you, these are the real results, the real test results. So that is the reason I didn't define them as a function of, for example, ZID or anything, because I didn't want to ruin the results. These are the real results from the field and from the lab. So you need to decide. And as you can see, the result that I provided is for 1 meter borehole. So generally for the design of the road, that 1 meter would be sufficient. And about the test results, the demonstrators of the course already explained you during the demonstration time. Here you can see the reclaimed soil results. I only provided you CBR. So simply based on the CBR value, you can determine the design CBR and use that later for your design. But for natural soil, as I mentioned, we need to conduct 3 different types of tests. That is the reason I provided you with the dynamic cone penetrometer test results, with laboratory CBR test results, as well as the particle size distribution or classification test results. And one student also asked about these test holes. When I mention here that test hole 1, this test hole 1 is the same as this one for particle size distribution. So we took a sample and we conduct sieve analysis, right? So this is the field test, CD, DCP test that we conduct. And we took a sample from that borehole, brought it to the lab and conducted sieve analysis and Atterberg limit test. And again, here, the test hole would be the same. It's the same as the other one. So the names are the same and consistent. So for DCP test in Excel sheet, can we consider 3 layers? Calculate CBR for each layer? It is totally up to you whether, so as I mentioned, this is based on the engineering judgment, right? You can get some ideas from these results that whether the soil that you are dealing with is a layered soil or it's a uniform soil, right? And then determine the values. But eventually, when you consider layered soil and calculate for different layers, eventually you need to come up with one design CBR for dynamic cone penetrometer test. So in the test type 3, is the test hole 4 same as test hole 2? Test type 3? Yes, for example, when I say that test hole 1 is the same as this test hole 1 and the same as this test hole 1. So they are the same. For assignments, can we turn in handwriting results or it has to be typing? It has to be typing. You can still add some handwritten as an appendix, but the report should be in a technical form. It should be a technical report, the same as the thing that you want to submit, you later submit in practice. So I provide you the details for each part. So I'm not going to define any marking criteria for that one. But during the first and second assignment, I'm going to provide you some feedback in order to improve your work for the final submission. And the last question, and after that we can have 5 minutes break. Then I will explain you about the design traffic. So let me answer the last question here. Basically, test holes of test type 2 and 3 are from test type 1 location. So the thing is that here we conduct a field test. From that field test, from borehole 1, we took sample, right? We brought it in the laboratory. We conducted particle size distribution test, sieve analysis, as well as CBR test. So you look at here, the tests are laboratory CBR. So we took a sample from borehole 1, brought it here and conducted sieve analysis as well as CBR test. All right, so let's have a break for 5 minutes, and after that, I'm going to talk about design traffic. All right. So let's continue the rest of the lecture. At the end of the lecture, I'm going to go through your questions and we can discuss different parts of the project if you want. So the second part of the project is about the design traffic. So you remember that first we talked about the subgrade evaluation. Then we want to design the access road. Therefore, we need to know what is the design traffic. How many vehicles are going to pass through this road during its design life? Which type of vehicles? What are the loads? So this is the thing we want to determine. In order to design the pavement, the structural design of the pavement, there are there are actually three input data that we need. First, we need to know what is the CBR value of the soil or the strength of the soil. The other thing is that which type of material we want to use for different layers, sub-base, base layer, as well as the surface layer, which type of pavement and which type of material we want to use. And the other thing is that what is the design traffic? So these are considered as the main elements or main input data for the design of the pavement. This is the chart from Astros for empirical design of pavement. So if you look at this table and this chart, the vertical axis on the right-hand side is CBR. So the CBR value, when the CBR value is decreasing, for example, from 15 to 10, the thickness, which is this distance, the thickness should increase from this value to this value. The other parameter which significantly affect your design is the design traffic. So look at here. When the design traffic is 10.10 to the power 6 or 1 million ESA, the unit is equivalent standard axle, the thickness is something around 600 millimeter would be sufficient. But when the traffic is 10 million ESA, then the thickness should be something around 780. So the main two parameters are CBR value as well as the design traffic. I will later tell you how to use this chart to design flexible pavement. But here I just wanted to show you how important are these two design parameters, CBR and design traffic. Now we want to know and determine the design traffic for the road. This design traffic is the function of number of the vehicles as well as the type of the vehicles passing through the road during its design life. So we have two important things. One is related to the types of the load, and the other one is the repetition of the load. For example, the types of the load can be different for different vehicles. We have the variability of the vehicles, as you know. We have the variability of the types of the vehicles. We have the variability of the load, the magnitude of the load, and even we have the variability in distribution of the load. For example, this example, let's consider a very simple example. As you can see, we have the same vehicle. The load is also the same, but the distribution of the load is different. So when these two trucks pass through the road, the effect of them on the road would be different. The level of damage due to the passages of this car would be different, right? Different effect on the road, or the level of deflection from these two vehicles would be different. The main philosophy in Ostroads is that we want to convert these different types of loads into one single unit. And that unit is considered as the equivalent standard load. So the main philosophy in Ostroads, as I wrote it here, is to convert loads of various magnitudes and repetition to an equivalent number of standard load. But before we determine this, before I define this standard load, how can we determine the number and the types of the vehicles? This is coming from the survey data or from the WIM survey, Way in Motion survey, that I will explain later. So about the vehicles, let's start, before I explain about the load repetition, let's focus on load types. The load types and the types of the vehicle passing through the road depends on the application of the pavement, the location of the road. What is the application of that pavement? Why do we design that pavement? For which type of vehicle? So, and the other thing which is very important is the heaviest vehicle passing through that road. So as a geotechnical engineer, as a pavement engineer, or as a civil engineer, when you want to design a pavement, you need to know what is the heaviest vehicle. You need to predict what is the heaviest vehicle. For example, for airfield, the heaviest vehicle depends on the type of the plane using that airfield. For most of the roads in Australia, the heaviest vehicle we consider is the road train, triple road train, or it can be different types of loads. So the pavement that you are designing must be strong enough to cater the heaviest vehicle. But what are the types of the vehicle that we need to consider for the design of a pavement? Based on Ostroads, we have 12 classes of vehicles. Here you can see different classes. The first two classes are considered as light vehicles, and from class 3 to class 12 are considered as heavy vehicles. Light vehicles, the contribution of light vehicles is very little. So the failure or the damage to the road because of the light vehicles is generally negligible. Because of that, when we want to design the pavement, we ignore the light vehicles. We only consider the heavy vehicles. When you want to determine the design traffic, we simply ignore the light vehicles. Even though the number of them are much, much more than the heavy vehicles, but the failure due to light vehicles is negligible. So we ignore that in the design. So for the design, we only consider classes 3 to 12. The other one, as I showed you, depends on the load distribution, how you transfer the load to the pavement. So this load distribution depends on the type of the axles or axle groups of the heavy vehicles. Here you can see different types of axles and axle groups. For example, here we have single axle, single tire, just one axle and one tire in each side. Single, we call it single axle single tire. The other one is single axle dual tire. Then we have triaxle tandem axle single tire, tandem axle single tire. Then here we have tandem axle dual tire, triaxle dual tire, and quad axle dual tire. Here I brought you the examples. So this is the single axle single tire. Simply you can see that. This is generally at front of the vehicle. At the back of the or at the rear of the vehicles, we generally have dual tires. So here you can see the single axle dual tire. Here you can see tandem axle single tire. Again, it's at the front. Here you can see the tandem axle dual tire. So it is tandem axle and it is dual tire, two tire. Here we have triaxle dual tire, and here you can see quad axle dual tire. So these are different types of axle groups that we have. So the distribution of the load depends on the type of the axle groups that we are using in each vehicle. All right, after defining different classes of vehicles, now we want to learn the first traffic parameter, and that's very simple traffic parameter. It is N parameter. It is the number of the axle groups per heavy vehicle, or NHVAG, number of axle group per heavy vehicle. And here you can see that, for example, for class 3, how many axle group we have for this vehicle for class 3? The number is 2, right? 2 axle group. So for class 4, can you tell me what is parameter N? Number of axle group per heavy vehicle. For class 4, this is 1 axle group. This is the second axle group. So again, it's 2. For this one, for class 5, this is again 2. These two are close to each other, therefore they are considered as 1 axle group. For class 6, can you please tell me what is parameter N? It is 3, thank you. For class 7, again it's 3, great. For class 8, again it is 3. For class 9, again it's 3. For class 10, can you please tell me? For B double, exactly, it is 4. Then class 11, 5. And class 12, here it is 7. So the first parameter is very easy, the number of the axle groups per heavy vehicle. As I mentioned, the main philosophy in Astrodes is to convert different types of loads and different types of vehicle or axle group to a standard load or a standard axle. But what is this standard load or a standard axle? Based on Astrodes, the standard load is considered as 8.2 tons, 8.2 tons or 80 kilonewton. This is considered as the standard load. And what is the standard axle? The standard axle is the single axle dual tire. And these are the standard dimensions. The distance between two wheels is 330 millimeter. And also the width between the dual tires is 1,800 millimeter. So this is the definition of the standard axle. So now we want to know how we can convert everything to this standard load and this standard axle. Also, we want to know what is the pressure for this standard axle. So the first thing we assume here is that we assume that the contact surface at the contact surface below one wheel is a circle. So we are considering a circular surface. And the diameter we consider for that one, for the standard wheel, is 92.1 millimeter. So we mentioned that the standard load is 80 kilonewton, right? So the load per tire is 80 divided by 4, it becomes 20 kilonewton. So it becomes 20 kilonewton here, 20 kilonewton here. We are considering uniform distribution. And it is simple to calculate the contact pressure. The contact pressure, the tire pavement contact pressure, becomes equal to 20 divided by the surface area of this circular area or circular surface. So you can simply divide 20 by the surface area of this circle, and the value that you derive is 750 kilopascal. So this is the tire pressure from the standard axle. But the question is that what if we have different types of axles? So they are not all, of course, they are not all single axle dual tire. What if we have different types? They conducted some tests in order to see what is the effect of, what are the effects of different types of axle? What is the damage from each axle? So, for example, for single axle single tire, when you apply 53 kilonewton, the level of damage or the level of deflection on the pavement would be equal to the level of damage of a standard axle, right? So if you apply this one, 50 kilonewton, apply 50 kilonewton to single axle single tire, the level of deflection that you get here, the level of deflection you get on the road would be equal to the level of deflection you get from this standard axle. And this is the standard axle. Single axle dual tire with 80 kilonewton. So these two are considered as equivalent. They are equivalent to each other. How about for tandem axle single tire? Again, they conducted test and they derive 89 kilonewton. If you put 89 kilonewton on that, you will get the same level of deflection. For tandem axle dual tire, the value is 135. And for triaxle dual tire, the value is 182 kilonewton. So all these loads that I showed you on different types of axles are equal to one standard axle, right? They are all equal to a standard axle simply because they are causing the same level of damage, the same level of deflection on the road. Let me show you one very, very simple example. So let's consider that we have one double road train, class 11, and the level of load on each axle has been shown. It is 53, 135, 182, and so on. And as you can see, if you compare it with this one, all these loads are equal to the standard loads, or equivalent to the standard loads. So we have 53 for single axle, single tire, 135, which is for tandem axle, dual tire, and so on. So the first thing we want to determine is parameter n. Can you please tell me what is parameter n? The number of axle group per heavy vehicle. So parameter n, yes, that's correct. Thank you. It is 5. It is 5 exactly, because we have 5 axle, 1, 2, 3, and 4, and 5. Now we want to determine the design traffic for the case that we have just one pass of this vehicle. Let's assume that this is just this vehicle just once passing through the road. So the design traffic for this case, since all of them are equal to one equivalent standard axle, the design traffic becomes equal to 5 ESA, right? So we convert everything to equivalent standard axle. And they are all equivalent standard axle, as I showed you here in the previous slide. So the design traffic becomes 5 ESA. And there is one parameter which is called damage index that we generally calculate when we want to determine the design traffic. And this is the case that we divide the design traffic by the parameter n, the number of the axle group per heavy vehicle. So for this case, the damage index becomes equal to 1. Now let me show you another example, example 2. So again, the number of the axle group per heavy vehicle is the same vehicle, so it is 5. But this time, look at the loads. The loads are not equivalent to the standard load, right? They are different. So last time it was 35, right? Look at here, it was 53. Or for this one, it was 135, but the load has changed now to 55 and 150. So the question is that if the load is different, and generally it is like that, it is not exactly the same as the standard load, how can we determine the design traffic, right? For just this one double road train. In order to determine this value, the method that we are using is this empirical equation. It is just one simple ratio. It is an empirical equation coming from the field tests. So in this equation, in order to convert everything to equivalent standard axle, we divide the load with the standard load. And then we consider this value to the power 4. So this is one empirical equation. Lij is the load, and Sli is the standard load. So the easiest way is to get back to the example and show how this equation works. This is the current load, 55. So this one is Lij, right? And this is the standard load. This is Sli that we are considering. So simply, we can use this empirical equation to change and convert everything to equivalent load. So it is 55 divided by 53 to the power 4. So this time, in order to calculate the design traffic, you need to use this empirical equation, 55 over 53 to the power 4 plus the second one, third one, and fifth one. So eventually, the equivalent standard axle becomes 6.6. What is the damage index? Again, the equivalent standard axle or the design traffic divided by parameter n, the number of the axle group per heavy vehicle. So it becomes 6.6 divided by 5. It gives us 1.32. And this is called damage index. So far I showed you the equation for the case that we are just dealing with one vehicle. But if we have more vehicles, and of course we have more vehicles, this is the equation to use in order to calculate the damage index. So later at the end, I'm going to show you one example, and in that example, I will show you how to use this equation. But for light traffic road, there is a table that you can use, and there are some presumptive values. So this is the damage index, as you can see here. And that damage index depends on whether you are designing the road for a rural area or for an urban area. For a rural area, the presumptive value is 0.9. For urban area, the presumptive value is 0.7. So for light traffic roads, you can simply use these two values in order to determine the design traffic and damage index. Also, there is a maximum limit. There is a legal limit for the loads. For example, for single axle, single tire, for the roads in Australia, the maximum load is 6 ton. Or for single axle dual tire, it is 11 ton. So the value cannot get above this value, right? Otherwise, the level of damage won't be acceptable to the road. So for different types of axle groups, we have different values of maximum limit. So far, we focus on the types of the loads, vehicle loads. In the second part, we want to determine the load repetition, the repetition of the load, right? How many times the vehicle passed through the road. For this one, we define a new parameter, which is called NDT. So for the first one, we define damage index, and we calculated damage index. For load repetition, we define NDT. What is this NDT? It is number of heavy vehicle axle groups passing the design lane during the pavement design life. So I'm going to show you, and I'm going to show you how to determine this one and what is the meaning of this sentence. So about the load repetition, for determination of this NDT, this is the procedure. First, we need to select a design period, the design life of the project. For example, it is 20 years, 30 years, 40 years. Then we need to determine the annual average daily traffic. After that, the percentage of heavy vehicles, because the important thing is the percentage of heavy vehicles. The light vehicles won't affect our design. Then lane distribution factor, LDF and DF parameters. After that, cumulative growth factor. Then we need to determine parameter N that I already explained you, the number of the axle group per heavy vehicle. And by having these 6 terms, we can determine NDT. Starting from the first one, what is this design period? The design period The classical or the definition in ASTROADS is the time span considered for the road pavement to function without major rehabilitation or reconstruction, right? So if we have major failure in the road prior to the design life, it is considered as the failure of the design, right? So prior to the design life, we shouldn't have any major rehabilitation or reconstruction. And we should note that resurfacing is very normal. Resurfacing is not considered as major reconstruction. So during the design life, we can have resurfacing, but we shouldn't have major reconstruction. How can we determine the design traffic? That depends on the importance of the road as well as the available fund. Here are the suggestions. Here are the values in ASTROADS. For flexible pavements, the design life is between 20 to 40 years. For rigid pavement, it is 30 to 40 years. So this is the first term. Second term is annual average daily traffic. The annual average daily traffic is the daily traffic, the average daily traffic that we are talking about. And it contains both the light and heavy vehicles. It is coming from the traffic survey, right? So we need to conduct traffic survey to determine this AADT. This daily traffic is for the first year of the first year service of the road. How can we determine this traffic survey? This traffic survey can be done on one existing roadway, and that road can be the road where the pavement is to be constructed, if that's the existing road, or it can be nearby road with similar travel pattern, right? So we need to conduct traffic survey on an existing roadway, and the existing roadway is either the road where the pavement is to be constructed or the nearby road with the similar travel pattern. Also, the traffic survey data that you use must be recent. You cannot use the results of 10 years ago. It should be recent, and also it should be obtained without any interruption. If there is any interruption, then it won't be reliable. The results cannot be used. For the survey, we are generally using the weigh-in-motion system. So the system you can see here, they scan the vehicles, all types of vehicles when they are moving, and the data that we are getting is the weight of the vehicles, speed of the vehicles, as well as the type of the vehicles. So for a period of time, for example, for 6 months, we gather the data and we use that one for the design and for determination of these annual average daily traffic. After this, we need to determine the percentage of the heavy traffic. And again, this percentage of heavy traffic is coming from the survey. So from the survey, we can determine the percentage of the heavy vehicles, right? Why we consider this one? Because in the design, we only consider the heavy vehicles. And we want to determine the average daily number of heavy vehicles in the first year. So simply you can multiply AADT by percentage of the heavy vehicles. Very simple, you can calculate this one. So percentage of heavy vehicle is very simple traffic parameter. No need to further explain this. There are two parameters, LDF and DF, that I'm going to show you here. DF is directional distribution factor. This is the proportion of traffic for each direction, right? So, for example, for this simple example, the proportion of traffic for each direction, for one direction is 47, and for the other one is 53%. So you can simply, by survey result, by having the WAIM survey result, you can simply determine parameter DF. If there is no survey results, for two-way roads, we can consider the presumptive value of 0.5, right? If that's a one-way road, then you need to consider the value of 1. The next parameter is parameter LDF, or the lane distribution factor. So when we want to design the pavement, we want to know what is the traffic for one lane, right? And generally, when we want to consider one lane, we need to consider the most heavily trafficked lane. In Australia and in most of the countries, the most heavily trafficked lane for heavy vehicles is the curb lane. And in Australia, it's the left lane or outside lane. So this is the table. So again, you can either use the survey data. If the project is important, you need to use the survey data. But if the project is not that important, if it's a light traffic road, then you can use the presumptive values from the Ostrows. Again, this is the table from Ostrows. It depends on whether you are designing pavement for rural area or for urban area. And it's the function of the number of the lane. For example, if you are designing a pavement for two-lane road, then you need to give all the heavy traffic to the curb lane, right? So in that case, LDF becomes equal to 1, the lane distribution factor. If it's, for example, urban area and the road is a 3-lane, then we assume that 65% of heavy vehicles are passing through curb lane. So therefore, the maximum value that you are considering for LDF in that case becomes 0.65. So lane distribution factor is the proportion of traffic assigned to a specific lane. And I should also mention that we always consider the same pavement configuration for all the lanes. So we don't change the pavement for different lanes. That is the reason we are considering the most heavily trafficked lane for determination of LDF. Next term is the cumulative growth factor. So of course, the traffic will change by time. So for the first year, we conduct some survey and we derive some data. But now we need to predict the traffic for the second year, for the third year, right? Until the end of the design life. So during the design period, the daily traffic is likely to change. And in order to calculate that one, we need to define the rate of annual growth. And eventually we need to calculate the cumulative growth factor. So there's an equation from statistics. You're all familiar with this equation, that how we can determine the cumulative growth factor over the design life. In this equation, P is the design life of the road. So you can either use this equation to calculate CGF, or you can use this table. This table is coming from this equation. The next term is to determine the number of the axle group per heavy vehicle. I already explained you that one. This is a simple definition. The number of the axle group per heavy vehicle. So again, we calculate this one based on the survey results. If they are not available for light traffic roads, you can use the um, presumptive values from OSTRUDS. And eventually, by having these terms, you can determine parameter NDT, which is the cumulative heavy vehicle axle groups or the load repetition. So this is the final equation that we have for determination of NDT based on the terms that I explained you. So we have average annual daily traffic, or we can call it daily traffic, right? This is the daily traffic for one day. If you multiply this value with 365, it becomes annual traffic. It is easy. Now annual traffic, if you multiply it by DF, right, it shows the annual traffic in one direction. So it becomes annual traffic in one direction. If you multiply it by percentage of heavy vehicle, it becomes the annual traffic of heavy vehicle in one direction. So because AADT included both heavy vehicles as well as light vehicles. So we need to multiply it by the percentage of heavy vehicle to calculate the annual traffic of heavy vehicles. But this is for the whole direction. If you want to determine it just for one lane, because I mentioned that we need to determine the traffic just for one lane, then you need to multiply it by LDF. So this will give you annual traffic of heavy vehicles passing the design lane, right? So far, this value is for 1 year, for the first year of service. In order to determine the value for the whole design life, we need to multiply it by cumulative growth factor. So it becomes traffic volume of heavy vehicles passing the design lane during design period, right? But parameter NDT, look at the definition of parameter NDT. It is the cumulative heavy vehicle axle groups, not the number of the vehicles. It is not the number of the vehicles, it is the number of the axle groups, right? The important thing is not the number of the vehicles. We want to know how many axle groups passing the road. So eventually we need to multiply that one with the number of the axle groups per heavy vehicle. And we reach to that definition that I showed you before. NDT is the number of heavy vehicle axle groups passing the design lane during design period. Let me show you one example, and after that, if we have enough time, I don't think we have enough time to go through example 2. So I will go through just example 1, and after that I will answer your questions. So let's assume that we have one rural road. We want to design, for example, pavement, and we want to determine the design traffic for a rural road. The annual average daily traffic is 20,000. The percentage of heavy vehicle is 12%. The annual growth is 3%. This is R. The number of the lanes is 4, 2 in each direction. And the design period is 30 years. We want to determine the design traffic for the thin asphalt on unbound granular. This is for the case that the mode of failure is rutting and permanent deformation. So we want to determine the design traffic First of all, we calculate CGF, the cumulative growth factor. So from statistics, we have this equation. P is the design life, which is 30 here, and R is the annual growth rate, which is 3. So you can simply substitute and calculate the value. CGF becomes 47.5. Next step is to determine DF and LDF, the distribution factor, the lane distribution factor, as well as the direction factor. So this is considered as a rural road. So it's a rural road. It's 2-lane. It was mentioned in the question. You need to consider the maximum value for LDF. So the left lane or the curved lane generally has more traffic. So it becomes 1. So LDF is 1. How about DF? DF, we already mentioned in the question. It's a 2-way traffic. Since there is no survey data or survey result, then 2-way traffic, we divide it to 2. We give 0.5 to one direction, 0.5 to another direction. Step 3 is determination of the number of axle group per heavy vehicle. Again, here we don't have survey results. We can use the presumptive value. So from the table, for rural area, it becomes 2.8. Now we have all the terms to calculate NDT. So for NDT, this is the equation. You can simply substitute the value and we reach to 5.8 times 10 to the power 7 heavy vehicle axle groups. So this is the number of the heavy vehicle axle groups passing through this road. But this is not enough for us. We want to convert everything to equivalent standard axle, right? Since we don't have any survey result, again, we can use the presumptive value. For the overall damage of the pavement, for rural area, the damage index is 0.9. So you can simply calculate the design equivalent standard axle as multiplication of the damage index by NDT. So it becomes 0.9 multiplied by 5.8 times 10 to the power 7 heavy vehicle axle group. And the design traffic becomes 5.24 times 10 to the power 7 equivalent standard axle. And this is the design traffic when you want to design the road based on the empirical equations. And for the case that you want to consider the rotting mode and loss of surface shape for the pavement. So this is for the rotting mode of damage. All right. So that's all for today. I will go through example 2 and explain the project, the data that I uploaded on Moodle next way. But the demonstrators will also go through example 2 for you and explain the details of the Excel I uploaded on Moodle for you during the demonstration time. So please attend the demonstration classes. And now, if you have any questions, please write them down in chat and I will go through them. So let's get back to your previous questions. The question is, do we have class distribution for borehole 4 in test type 3? So let's get back to subgrade evaluation. For subgrade evaluation, soil test. So these are all the data that I provided you. No, I didn't give you, for particle size distribution, I only gave you test borehole 1 and borehole 2 input data. So there is no for borehole 4. So do we need to briefly write up the project description for assignment 1? Assignment 1 is only about a strengths evaluation, about the subgrade strengths evaluation. So you don't need to describe the whole project in it. Just focus on a strengths evaluation. Basically, test holes of test type 2 and 3 are from test type 1 location. Yes, as I mentioned, for example, in test 1, I wrote borehole 1. So this borehole 1, the soil we are using here for type 2 and type 3 are from borehole 1, right? So when I say borehole 1, this borehole 1 and the type of the soil is the same for all of these, right? For all 3 types, borehole 1 has the same meaning. So I think I already answered the other questions, but now let's get back. So how can we define the drainage condition for hole 4? For borehole 4, again, you need to decide about this unsoaked or 4-day soaked based on the environmental condition of the problem, right? The project. So just go through that part that I explained you, CBR test and the drainage conditions. You can also go through the standards, and that will provide you with more details about that one. So eventually you need to decide whether you need to consider the results of the unsoaked CBR or 4-day soaked CBR. So I could not find the stabilization table in the standard. Could you please tell us the source of it? So I brought these from different sources. Some of them are from main roads that I already gave you the link in the introduction. So you can find very useful information in main roads about that. Yeah. So yeah, that one is from main road. So do you have any other question about design traffic or subgrade evaluation? All right, great. Thank you very much. So please attend the workshops on Thursday and Friday based on your time slot, and the demonstrator will further explain the details about the project and will help you with different parts. All right, thank you very much for your attention. Have a great night. Cheers.